So decrease and conquer, the first algorithm that we look at is a sorting algorithm called insertion sort. Okay. So in insertion sort, what we have as usual is an array. So let's assume that we have an array A. So we have n objects from A0 to A n minus 1, right? So this is my array. So the way I will sort this is I will first sort the segment from 0 to n minus 2. So I will decrease, and hence the term decrease and conquer. I will decrease the array by one element, sort it, and then I will go back and I will look for an appropriate position to insert the last element so that the overall array remains sorted. So before we look at the mechanics of how this happens, we should just notice that this is quite a natural algorithm. So this is probably the algorithm that we often use instinctively when we need to sort something. So imagine, for instance, a shuffled deck of cards. Right? So we have a deck of cards and we now want to sort it out in ascending order in each suit. Right? So what we will typically do is we'll pick up the first card. Then we pick up the second card. If it's bigger, we put it behind. If it's smaller, we put it in front. So now we have a sorted deck of 2 cards. We pick up the third card, insert it in the correct place between these 2 cards. Now we have a sorted deck of 3 cards, and so on. So at every point we have a sorted deck in our hand. We pick up the next card and we insert it in the correct place. So this is the insertion sort. So we're doing insertion sort by building up a larger and larger sorted collection. And at each point we insert a new element into it. But inductively we would write it as saying that we sort A of 0 to n minus 2 and then insert A n minus 1 into it. So we have this sorted segment from A0 to n minus 2, and we have this last element which has to come into it, right? So now how do we insert it? So one option is to insert by looking from the left hand side, right? So we are assuming, let us say that it is in ascending order, for example. When we are looking from the left hand side, we find the first position where it fits and we do it. So that is one option. The other option is to do it from the right hand side, right? So both of these are equivalent, except that if the array was in ascending order already and we start from the right, then very quickly we'll find that we have to stop and do it here. So for almost sorted arrays, it's generally better to do it from the right. Similarly, if it was in descending order, then we'll find that this is already smaller than the last element. So if we go from the right, it will stay where it is. Whereas if we start from the left, we'll have to walk all the way to the end to find that it should have been exactly the same place that it is now. Right? So generally, searching from the right for the position to insert is the obvious thing. So this is the straightforward insertion sort. But of course, we could also use binary search to speed up the process, right? So we could first check from here whether the midpoint is bigger or smaller, and then depending on that, we could either go to the midpoint there or the midpoint here. So using binary search in log n steps, we'll find the position where we would like to insert the element. But the point, of course, is that having found the position, we still have to shift everything. So in the worst case, we would have to shift a lot of elements in order to make space. So it doesn't really help in the overall complexity much. But we could use binary search to find the position to insert as well. So before we look at the formal algorithm for insertion sort, let's work out by hand how it would operate on this sequence of 7 numbers. So we start with this unsorted array, and initially we will start from the left end and start with an array of size 1 which is trivially sorted. So we have an array of size 1 consisting of the first element 89, which is trivially sorted, and now we will take the next element and we will try to insert it into the sorted list. So now it's clear that 45 goes before 89, so now we have a sorted segment with 2 elements, and now we need to take the next element and try to insert it. So we walk backwards, so we try to see, and we see that 68 is smaller than 89, so it has to go to the left. We come to 45 and we find that 68 is bigger than 45, so we find that the insertion point is in between the two. So at the next step, we now try to insert 90, and then we find that it's immediately bigger than 89, so we keep it as it is and we grow the segment by 1 more. So now we continue with our procedure. So the next thing to do is insert 29. So having inserted 29, then we would insert 34. So we'd again go back and we'd find that this is the place that 34 should go. And finally, we'll insert 17, and again it has to go all the way to the end. And at this stage we are done. So we have a sorted array. So we started by taking the first element, sorting the second element by putting it in the right place, then took the third element, put it in the right place, and so on. So one by one we inserted elements into a sorted prefix until the entire prefix is sorted and we have no more elements to insert. So here is a formal statement of the algorithm. So we start, as we saw in the example, from 1 to n. What we do is we choose the value v to be the one that we are going to insert. So what we start with is the position before the one. So we have basically at any point, we are assuming that we have sorted from 0 to I minus 1, and we are currently looking at position I. So we need to figure out where we want to insert this. So we start when j is equal to I minus 1, and then we walk backwards, and so long as a of j is greater than v, so this is our value v, okay, so long as a of j is greater than v, what we do is we shift a of j to the right. We move a of j to a of j plus 1, and we walk back one more step. And eventually when we are, so basically every value as we walk past is moving to the right, and eventually we will hit a point where a of j is less than or equal to v, and at this point we can insert v, so we say a of j plus 1 is v. Right? So this is the basic algorithm. It's a very simple algorithm, and this is how it works. We already seen how it works rather. So it's not very difficult to analyze the worst case complexity of this. Okay, so the outer loop, we have a we do it once for every element in the array, so it's n times, and inside we have to do this linear scan, right? So this is order I for iteration I. So when we have done a0 to ai minus 1 and we want to insert ai, we have to in general walk through all of them. If it is the smallest value, it must walk through all of them before we find it. So for iteration I, we take order I time. So basically we have the standard thing, which is 1 plus 2 plus n minus 1 steps, and this is going to be theta of n squared, as we have seen. The real value, as we will need to point out, is actually n into n minus 1 by 2. So this is important because we will think about average case in a minute. So in the worst case, it is theta of n squared, and there's just a simple analysis based on the linear scan n times. Suppose we had used binary search instead of a linear scan to decide where to insert ai into the sorted array a0 to ai minus 1. In this case, what would the worst case complexity of insertion sort be? A O n, B O n log n, C O n squared, or D O n squared log n? Well, the answer is that the worst case complexity remains O n squared. First of all, the outer loop still runs n times. And inside the loop, for each I, we speed up the time it takes to determine the insertion point. By using binary search, we take only log I steps to find this point. But when we do a linear scan, while we are searching for the place to insert, we are also shifting elements to make one empty slot free for AI. Now in binary search, this doesn't happen. So we find the position to insert, but then in the worst case, if the insertion point is at the leftmost end of the segment a0 to ai minus 1, we have to shift every element right by 1, and that takes oi times. So in the worst case, again we have a summation of 1 plus 2 up to n minus 1, and so the worst case remains O n squared even if we use binary search. So we have seen that there is a best case in this particular situation. So the best case is that if it is already sorted, right, then each insert takes us only one step. Okay? So it is a constant. Basically, we look at the element and it goes immediately where it is, and therefore we have a best case complexity of order n. So what is interesting in this is that you can do an average case analysis. We will not go into the details of how you compute it, but it turns out that the average case is actually n into n minus 1 by 4. Okay. So it is still theta of n squared, right? But the important thing is that this 4, so it is half the worst case. Okay, so the worst case, you remember, was n into n minus 1 by 2. Right? So the average case is theta of n squared, but it is half the worst case. So it turns out that actually insertion sort is quite effective for small arrays. And of course, the best case says that it's good for almost sorted arrays. See, small arrays cannot be very disturbed because they are small. So for instance, typically one would take some algorithm like quicksort. Okay, and then when the interval becomes, is say less than 10, okay, then you switch to insertion sort. So the natural recursive definition of quicksort says you keep going down all the way until your interval length is 0 or 1. But in practice, what you could do is you could put a larger window and say once it crosses 10, you don't again recursively call quicksort, but rather you use insertion sort to quickly sort it. There is another variation of insertion sort called shell sort, or more accurately Shell's sort, because it was invented by a person called Shell, and this is used to, for instance, sort moderately large files. Okay. So insertion sort is an example of decrease and conquer. It has worst case theta n squared, and more accurately n into n minus 1 by 2. It has a best case of O(n) when it's already sorted. It has an average case which is also theta n squared, but it is n into n minus 1 by 4, and therefore it is half the worst case, and it is good for small arrays, and so we can use it as a base case for something like quicksort.